Hello dear students, welcome back to the lecture series Theory of Semigroups. In this lecture we are going to discuss monogenic semigroups, or we can say cyclic semigroups. As in case of groups we have cyclic groups, and same in this semigroups we have a cyclic semigroup, or we also call it monogenic semigroups. Okay. So as you know that in case of groups, the intersection of two subgroups is again a subgroup, but in semigroup it's not true in general. So it's true, we have to impose some condition on that class of sub-semigroups, so that the intersection of those sub-semigroups will be a sub-semigroup of a given semigroup. Okay. So let's discuss it in detail. So let S be a semigroup. Let S be a semigroup. Let S be a semigroup, and we have a family of sub-semigroups, and let I is in the index set I. It's the family of B and family of be a family of sub-semigroups of S. Then their intersection. Then this intersection of UI's I in the index set I is a sub-semigroup. Is a sub-semigroup. Is a sub-semigroup of S if the intersection is non-empty. If the intersection UI I runs from I is in the index set I is not equal to 5, it's non-empty. So intersection of sub-semigroups is a sub-semigroup only if this intersection is non-empty. Otherwise it's not true in general. For example, so let's take an example of two sub-semigroups of a given semigroup, and we will show that their intersection is not a sub-semigroup. So example of, so let's take n. Let's take this n with respect to multiplication is a semigroup. Then these even natural numbers with respect to multiplication and odd natural numbers with respect to multiplication is again a sub-semigroup. Then and these what is again are sub-semigroups. This is a semigroup n with respect to multiplication, and these two set of even natural numbers with the same operation and set of odd natural numbers 2n plus 1 with this multiplication operation, they are sub-semigroups of n. But this is clearly because product of two even natural numbers is again a natural number, product of two odd natural numbers is again an odd natural number. So that's why these two are both are sub-semigroups of n. But their intersection 2n plus 1, it's empty set, it's not non-empty. So that's why this condition is required there, that their intersection should be not equal to 5. It should be non-empty. Then we can say this intersection is a sub-semigroup. So in some cases the intersection may be empty, like this in this example. Okay. So let's now discuss the sub-semigroup generated by some particular set. Let S be a semigroup. Let S be a semigroup and A be subset of S. It's a non-empty set. It's a subset of S. Then we take the class of all subsemigroups of S containing A. Subsemigroups of S containing A. So let's take this class. Let UI, I is in the index set I, be a family of subsemigroups of S containing A. So that is this A is subset of UI for all I and I. So therefore the intersection, because A is subset of each UI, so therefore A is subset of intersection UI, I is in the index set I, because it is subset of each UI, which implies, because since A is non-empty set and it's subset of this intersection, so that implies intersection UI, I and I is non-empty. So therefore this intersection is a subsemigroup. Therefore the intersection UI's I and I is the subsemigroup, is a subsemigroup of S containing A. It contains A. Containing A. And we denote it by, this notation. Okay. Then we see some certain properties of, actually it's the smallest subsemigroup of S containing A. So then one can easily verify that. Then one can easily verify, because it is the intersection, actually intersection of all subsemigroups containing A. Then one can easily verify that this subsemigroup, which is actually the intersection of all subsemigroups of S containing A, is the smallest subsemigroup of S containing A. Subsemigroups of S containing A. So in other words, it means that it means that given any subsemigroup of S containing A, then this subsemigroup, which is the intersection of all subsemigroups of S containing A, is subset of that subsemigroup. Okay. So it means that given any subsemigroup, given any subsemigroup U of S containing A, this subsemigroup, that it's subset of U. It's the smallest one. It's the smallest subsemigroup containing A. That means given any subsemigroup U of S containing A, then this subsemigroup, it's subset of U. You can easily verify it. It's not too difficult. And we can see that. So one can easily verify that this subsemigroup is actually the set of finite products of elements of A that we need to verify, actually. Okay. So that's an exercise of actually if A is not equal to 5, then you have to show that the semigroup, the smallest semigroup containing A, it's actually equal to this A1, A2 up to AN, where these AIs, they belong to A, 1 less or equal to I less or equal to N. So in other words, you have to show that actually this one, it is the smallest sub semigroup of S containing A. This is already this is the smallest sub semigroup of S containing A. Now if you prove that this one, it is also the smallest sub semigroup of S containing A, then these two are equal. Then Then show that. So let's solve this exercise. So let's denote this by U. Let U is equal to this set A1, A2, 1 up to AN, where AIs, they belong to A, 1 less or equal to I less or equal to N. We need to show that this the semigroup A is equal to U. The smallest semigroup containing A is equal to U. So let's take any element in U. Let X belongs to U. We show that it's also in that. X is in U. This implies X is some finite product, because elements of U are finite product of elements of A. So X is equal to A1, A2, AN, where these AIs, they belong to A, 1 less or equal to I less or equal to N. Since these AIs, they are in A, and A is subset of this smallest subsemigroup containing A. Since A is subset of that semigroup, so therefore these AIs, they are also in that semigroup, because each AI belongs to A, 1 less or equal to I less or equal to N, and it is a subsemigroup. So therefore the product must be also in that. So which implies this X, which is equal to the product, finite product. It's in that. So any element X in U is in that semigroup, smallest semigroup containing A. So which implies U is subset of A. U is subset of A. U is subset of. Now we prove that this one, it's also subset of U. So to prove this, we show that this U is a subsemigroup of S containing A. U is a subsemigroup. That's trivial because it's the set of finite products. You can easily verify it. This U, it's a subsemigroup of S. This is easy. It's not too difficult. It's very simple. So this is subsem, because if you take any two elements from U, both elements are the finite products of the elements of S, say A1, A2, AN, B1, B2, BN, then their product is again the finite products of elements of S. So that means this is a subsemigroup. So we show that this subsemigroup, it contains A. It contains A. So next we show that U is a subsemigroup of S containing A. So let's take any element A in A. Then A is itself the finite product because it's the single element. So which implies A also belongs to U, because U contains all the finite products of the elements of A, and A is itself the finite product because it's a single element, single one product containing only one element. A belongs to U. So so therefore U is a subsemigroup of S containing A. So which implies A is subset of U. So that means U is a subsemigroup of S containing A, but this one, it is the smallest subsemigroup of S containing A. So therefore U is a subsemigroup of S containing A. This one, it is the smallest subsemigroup of S containing A. So that means this must be subset of U because it is the smallest one. Now we conclude from these two. Here we have shown that this U is subsemigroup of the smallest subsemigroup containing A. So U is subsemigroup of this. U is subset of this. And here we have shown that this smallest subsemigroup of S containing A is subset of U. So let's name it first here. Name it first here. This one A is sorry, it's not this one. Name it first. This U is subset of this. U is subset of this. Name it first. Okay. And name this inclusion as second. So from first and second, we conclude that smallest subsemigroup of S containing A is equal to U, which is the finite products of the elements of A. So that proves this exercise. Now next, if this A is a subset of S, if it is a subset of S such that the subsemigroup, smallest subsemigroup of A, S containing A is equal to S whole. If A is subset of S such that the smallest subsemigroup of S containing A is equal to S, then we say this S is generated by A. Then we say S is generated by A. Or this semigroup, it's called the subsemigroup of S generated by A. Okay, this semigroup, which is the smallest subsemigroup of S containing A, it's called the subsemigroup of S generated by A. Now, in case A is a subset of S such that the smallest subsemigroup containing A is equal to S, then we say this S is generated by A because S is equal to the subsemigroup generated by A. Then we say S is generated by A. In general, this notation is a subsemigroup of S generated by A. So in case it is equal to whole S, then we say S is generated by A. Now in particular, if this A is a singleton set, if A is equal to singleton set, then the subsemigroup generated by A, it is equal to the, as we have shown that it's actually equal to the all the finite products of the elements of A. But here in this case, A contains only one element A, so it's like this: A, all the finite products, then A into A, this A square, A into A cube, A into A power 4, and so on. All the finite products of the elements of A. And A contains only one element A, so we have to take the products of A with itself. All the products. A into A into A into A, then 4 times. So it's A square, A cube, A4, and so on. And this is also denoted by this notation in case of singleton set. Okay. This subsemigroup generated by a singleton set is called the monogenic subsemigroup. That subsemigroup generated by A, generated by singleton set, this A is called monogenic subsemigroup of S. Monogenic subsemigroup of S. Now, in case this S is equal to this whole monogenic subsemigroup, in case S is equal to this whole, As in case of groups, if there is a single element A such that G is generated by that element A, then we call such groups cyclic subgroups. So here, if we can choose an element A in S such that the sub-semigroup generated by A is equal to whole S, then we say this S is a monogenic semigroup. So that's if we can find an element A in S such that the sub-semigroup generated by A is equal to whole S, then we can say this S is a monogenic semigroup. Then we say or cyclic semigroup. We use term here monogenic semigroups. It's a more familiar. So we say S is a monogenic semigroup generated by A. Okay, thank you.